This is lecture 3 of this video lecture series on the mathematical prerequisites for quantum mechanics. And today the main topic of discussion is linear operators. So towards the end of the last video lecture, I introduced the concept of linear operators as in just objects which act on a vector in your vector space and then transform it. So they take one vector and they move it to some other position. So it takes a vector v and acts on it and returns some other vector v prime. And we saw some examples in simple R2 where you can have the identity operator which just leaves your vector intact, or you can have an operator that stretches or shrinks a vector. You can have a rotation operator, you can have a reflection operator. Then of course we are not restricted to working in R2, you can go to R3, Rn in general, and you can have combinations of various reflections about various axes, rotations in various planes, stretching, etc. So your most general operator will just take vectors from one point and move them somewhere else. So in general, so if you remember, any vector I can represent as in terms of certain components vi and the basis vectors I. So just these i's are the basis vectors. So if I want to know the action of the operator on any general vector, what I can do is I can just find out what the operator does to the basis vectors. Then in terms of that, I can find out what it does to any other vector. So if I know that omega acts on every I to give some I prime, then I can tell that when omega acts on v is just summation I, vi with I, but the vi's are just some numbers and omega is a linear operator, so I can pull the numbers out. So I get and I know that omega I is I prime. So if I know what omega, if I know what all the I primes are, then I know what my final v prime is. So then v prime, which I am defining as omega operating on v, is just given by this formula. So let's take an example. Suppose I take my operator omega is 0, 0, 1, 1, 0, 0, 0, 1, 0. And I want to find out what action this takes on any vector v in my vector space R3. So I'm going to choose my basis vectors as 1, 0, 0, and I'll refer to this as 1, 0, 1, 0, which I will refer to as 2, and 0, 0, 1, which I will refer to as 3. So let us find first what is 1 prime, 2 prime, 3 prime. So 1 prime is just omega operating on 1, which is 0, 0, 1, 1, 0, 0, 0, 1, 0 operating on 1, 0, 0. This turns out to be what? 0, 1, and 0. Very good. Similarly, you can check that 2 prime is omega operating on 2, and this is going to give me, I think, 0, 0, 1. Yeah. And similarly 3 prime is omega operating on 3, which will give me 1, 0, 0. Work it out, verify these for yourself. So then, given some vector v, let's call v as 2, minus 3 and 5. So if I want to find what is omega, so this is what, 2 times 1 plus minus 3 times 2 plus 5 times 3. So then V prime is going to be the same coefficients but with the primed basis vectors. So over here you put 1 prime, 2 prime, 3 prime and see what you get. And also verify just by doing direct matrix multiplication. If you just do omega with the V vector, just check that both ways you get the same answer. That's what you should find. You should verify that this formula over here holds. So a simple calculation just involves matrix multiplication. Okay. What if I have two operators and I want them to act on a vector V? So I'm talking about products of operators. So let's say my operators are omega 1 and omega 2. So I want to find out what is omega 1, omega 2 acting on V. So first omega 2 will act on V. So when omega 2 acts on V, you will get some vector, some other vector. And then omega 1 will act on it. So if you want me to write it explicitly, omega 1 operating on omega 2V. And I'm just denoting this entire thing. Instead of calling it V prime, I'm just writing it like this. It's just a notation that omega 2V is just a name that I'm giving to the vector. It doesn't mean anything more than that. You will notice that, see, these omegas, they are operators, so they are like matrices, right? And matrix multiplication doesn't commute. If you change the order of two matrices, in general, omega 1 into omega 2 is not going to be equal to omega 2 into omega 1. Which means omega 1, omega 2 operating on a vector V is not going to be the same as omega 2, omega 1 acting on the vector V. Or omega 1, omega 2 minus omega 2, omega 1 whole thing acting on vector V is not equal to 0. So we have a special name for this object. This is denoted as square bracket omega 1 comma omega 2, and this is called, in words, this is called the commutator of omega 1 and omega 2. So in general, you should expect that the commutator of any two operators in general is not 0. Let's take an example. In R3, I'll take omega 1 to be rotation by 90 degrees about the x-axis, and omega 2 to be rotation by 90 degrees about the y-axis. And you can verify for yourself just geometrically. We can do it right now. You can verify that omega 1 into omega 2 is not the same as omega 2 into omega 1. Let me take some object. Okay, so here in the little video inside, you can see I have with me a little booklet. Let's set up some coordinate axes. Okay, so here, yes, you can see it. Let's say pointing this way is the x-axis, pointing upwards is the y-axis, and pointing this way is the z-axis coming into the camera or towards the screen. So x, y, z. So let's rotate this in two ways. First, we'll do first omega 1 then omega 2. So first we'll rotate about the x-axis. So this is the x-axis. I want to rotate about this by 90 degrees. So it becomes like this. Okay. So this was the axis. I rotated about it by 90 degrees. Then I want to rotate about the y-axis. Y-axis is pointing upwards. If I rotate about this by 90 degrees, it becomes like this. Okay, so first x then y. Turn this booklet such that the spine is facing towards you and it's horizontal. Let's again start from the origin, and first we'll do y rotation, then we'll do x rotation. Y rotation is, y is this axis, so about this by 90 degrees. So it comes like this way, and then rotation about x. So x is here by 90 degrees. So this is 90 degree about x. So clearly this is not what we had before, right? Earlier when we did first x then y, the book looked like this. When we did first y then x, then the book looks like this. So clearly the effect of operating these two operations or these two operators depends on the order in which you do it. That means they don't commute with each other. If you change the order, you get a different result in the end. So that's a like an actual geometric illustration of two operations in R3 not commuting with each other. Okay, there are a couple of identities involving commutators. The first is that if you take the commutator of A with, so A, B, C are all operators. If I take the commutator of A with the product BC, this is B operate with the commutator AC plus commutator of AB with C. How do we prove it? It's straightforward actually. If you look at the right hand side, so this is B commutator of AC plus commutator of AB multiplied by C. So this is just B. Commutator of A and C means AC minus CA. Similarly, commutator of AB means AB minus BA. Now you must remember, when you're multiplying matrices, you make sure the order is exactly the same. Like B times AC, don't write it as ABC. It's BAC. BAC minus BCA plus ABC minus BAC. See, BAC cancels. What I have left is ABC minus BCA. And matrix multiplication is associative. So I can do this. So this is just A times BC minus BC times A, which is commutator of A with BC. This is what you wanted to prove. Similarly, exact same way, you can see what happens if the first two, the first matrix in the commutator is a product, and this turns out to be A BC plus AC with B, and the proof is exactly along the same lines. Just take the RHS, open it up, you'll get the left hand side. So I leave it to you as an exercise to do this. What do you know about commutator of A with B and commutator of B with A? Obviously, these are negatives of each other, because one is AB minus BA, the other is BA minus AB. So that is just obvious. Okay. What about inverse of an operator? Can we define the inverse of an operator? Yes, we can. So for a given operator omega, its inverse which we denote as omega inverse is a matrix such that omega operating on omega inverse or omega inverse operating on omega gives you the identity. Of course, for example, if you are representing this operator as a matrix, not all matrices have inverses. So very importantly, you have to check that the determinant of the matrix is non-zero. Only then can you get an inverse. What about inverse of a product? So if I have two operators A, B, and if I want to take the inverse of this has to be B inverse A inverse. You can check that, because if I take AB inverse and then because AB into AB inverse will then be A B B inverse A inverse. B inverse is identity, so A identity A inverse, which is just A inverse, and then this gives you identity. Therefore AB inverse has to be B inverse A inverse. If I take AB and if I take the transpose of this matrix, this you can check is B transpose A transpose. Okay. The next question I want to ask is, so we write these operators as matrices. What are the elements of the matrix? So what is the 1 1 element, 1 2 element, 1 3 element, and so on? Elements of the matrix operator omega. See, we had checked when we were talking about vectors, and I wanted to find out what are the components of a vector. I took dot product of the vector with the corresponding basis vector. Something similar is going to happen over here. So for example, if I give you a matrix, let's say I give you a 3 cross 3 matrix, 1 2 minus 3 4 0 1 minus 2 1 3. Okay, let's call this omega. And if I ask you what is the 1 comma, no, this is 2 comma 1, what is the 2 comma 1 element of omega? You can check that if you want to extract this, you need to take omega and 2 comma 1. So you operate on this with 0 1 0 and 1 0 0. So this is basically your 2 and this is your 1. Do this explicitly. 0 1 0, and this operating on 1 0 0 is going to give me 1 4 minus 2, and then this is just 4, right? So in general, if you want the ijth element of any matrix operator, you need to take the operator omega, put the ket j on one side and put the bra I on the other side. So whenever you see an object like this is an operator or a matrix in the middle. On the left side you have a row vector, on the right side you have a column vector. so that in the end this is going to be like, so over here this is an n cross 1, no sorry, this is a 1 cross n, this is n cross n, and this is n cross 1. So in the end you have a 1 cross 1, which is a number, and that's the ijth element of omega. So whenever you need to find the element of a matrix, you squeeze it between a bra and a ket corresponding to the indices that you want. So omega, the ijth component, you put the I on in the ket side, the ith basis vector on the ket side, and the jth basis vector, sorry, ith basis vector on the bra side, jth basis vector on the ket side, and that will give you the element of this matrix. Now this also points to one very important fact, which is that the elements of a matrix or elements of an operator are basis dependent. So if I have an operator, then what numbers I write, the elements of the matrix, depends on what basis I'm choosing to represent it. If I change my basis, those numbers will change. Again, remember, I said this when I was talking about vectors also. A certain vector remains the same. So if you're talking about a physical vector like an electric field or an acceleration, the physical thing remains the same. The only thing that changes are its components, because you're choosing a different basis. The components of the vector are basis dependent, but the vector itself is the same. Similarly over here, the physical sense of the operator is the same. So if the operator represents a rotation by 45 degrees in the YZ plane, that's the meaning of that operator remains the same. Or if it is a stretching of vectors by a factor of 3, that fact will remain the same. However, depending on what basis you have chosen, the elements of the matrix operator might change. So this is a basis dependent fact. Okay. Let's say omega acts on the vector v to give me the vector w. I want to know how are the components of v and w related to each other. So let's choose some basis set and we'll call these i's. So I know that v I can represent in terms of the basis vectors and some coefficients. Similarly, w also I can write in terms of some coefficients and the basis vectors. Then the ith component of w is just w ket with inner product with bra I by definition. So this is I, but w is omega operating on v from here. So this is I omega v, but I know that the v's are v's are given by this. So I will write this as I omega summation I v. Oh, now see over here inside this there is a summation over I, but I already have an I outside, so I should use some different let's call this j. Doesn't matter, it's just a dummy index which I'm using to sum over these inside this. So it doesn't matter if I call it I, J, K, Sushant. I'll call that index whatever I want. So I'll call it J. Just to show that this summation index is not the same as this I over here. Alright, now what I can do is I can pull out these VJs. So this is summation J, VJ, and then I omega J. If you don't mind, I'll write the VJ on the other side. It's just a number, so it doesn't matter how I'm multiplying it. Now what is omega ij? This is what is I omega j? This is just the ijth component of the matrix omega. This is what we saw on the last page. This is the definition. So this is omega ij bj. So this is how the components of v and omega are related to each other. And you can check, this is exactly how we do matrix multiplication, no? What does this formula mean? It just means you write down your omega, all of its elements, then you write down your vj, and what this rule over here is telling you is you do this times this plus this times this plus this times this. So what this formula over here is telling you, and the formula in the box is telling you, is just how to do matrix multiplication. So we derive it by starting from the basis vector representation of the operators and the vectors. Okay. Same thing actually we can do also to see how we do matrix multiplication of two matrices. So for example, let A, B and C be operators such that C is AB. So this is matrix multiplication. I can ask the question, what do the elements of C look like? So if I look at the ijth element of C, this by definition is bra I C ket J, but C is AB. So I A B J. Okay, now if you remember in the last video lecture, so lecture 2, I had introduced one identity matrix over there, and I had said that identity is given by summation over I ket I bra I. So I'm going to introduce this identity over here in the middle. By the way, there's a name for this equation, and this is it's a result that one uses very often. It is called the completeness relation. Why is it called completeness? Basically, the sum is over all the basis vectors. If you miss out one basis vector, then the summation of this ket I bra I will not give you 1. It will not give you the identity matrix. So this only gives you 1 when you take the complete set of basis vectors. That's why this is called the completeness relation. So I'm going to introduce an identity in the middle of A and B over here. So it will become I A summation. Now I cannot put I or J because those are already there in the equation. I'm going to put summation K if you don't mind. So K B J. So I'll pull the summation out, and I have I, A, K, K, B, J, and this is just the I kth component of the matrix A, and this is just the k jth component of the matrix B. So this is your rule for multiplying two matrices. And you can again check what this just means is you write your matrix A over here, you write your matrix B over here, and it is the column index of K and the row index of B which you are summing over. So you are taking this times this plus this times this plus this times this and so on, and that will give you the ijth element of C. So this is the multiplication rule for matrices, again starting from the this kind of basis representation of the matrices.